Mount Etna's underwater collapse is accelerating, and what scientists discovered 1,200 meters beneath the Mediterranean waves is rewriting everything we thought we knew about volcanic disasters. May 2017. Marine instruments captured something impossible. Mount Etna's submerged southeastern flank slipped 4 centimeters in just 8 days. That is not slow geological creep. That is a mountain sprinting toward catastrophic failure. Here is what has scientists in complete panic. The movement is not from magma pushing the volcano apart. The seafloor data proves the opposite. Etna is collapsing from gravity itself. Billions of tons of volcanic rock sliding seaward, accelerating away from the volcanic center, following the exact pattern of every mega collapse in Earth's history. And the movement is not stopping. It is systematic, measurable, relentless. Catania sits directly in the collapse path. 300,000 people, minutes from impact. No warning system exists fast enough to save them. But here is the most terrifying question. If underwater monitoring just revealed Etna's invisible collapse, how many other coastal volcanoes are already failing beneath the waves? And which Mediterranean coastline will be the first to discover they are out of time? May 2017. The data comes back from the seafloor transponders, and Dr. Marilia Urlaub's team at the Geomar Helmholtz Center for Ocean Research stares at numbers that should not exist. Mount Etna's southeastern underwater flank moved 4 centimeters seaward in 8 days. The reading gets checked, rechecked, verified against every calibration protocol. The numbers do not change. To understand why this sends shockwaves through the volcanology community, consider this. Mount Etna's summit moves millimeters during major eruptions that make international headlines, the kind of eruptions that light up the night sky and draw thousands of tourists. Those spectacular displays produce tiny, measurable deformation. But that kind of movement from the underwater flank, that is not volcanic business as usual. That is geological sprinting. The Marine Geodesy network captures something even more disturbing than the speed. 5 seafloor sensors positioned across Etna's submerged southeastern slope record synchronized movement in a pattern that defies every volcanic model. The displacement accelerates away from the magmatic center, not toward it. The fastest movement occurs at the submerged fringes, easing toward motionless near the volcanic heart. Acoustic ranging measures the shifts with millimeter precision, and the data paints an unmistakable picture. This is not magma pressure inflating the mountain. This is gravity winning. For decades, volcanologists operated under a tidy assumption. Volcanic flanks move because molten rock pushes them apart from the inside. Magma intrudes, pressure builds, slopes bulge outward, eruption releases the tension. Repeat. The model explained most volcanoes most of the time, so it became gospel. But Etna's seafloor measurements shatter that gospel completely. The mountain is not being pushed. It is falling. The entire southeastern underwater flank is mobilizing under its own weight, sliding toward the Mediterranean abyss in a gravitational collapse sequence that matches every catastrophic landslide in geological history. And here is what keeps scientists awake at night. The movement shows no indication of slowing, no stabilization, no pause. Etna is stretching at the edges, and mountains are not supposed to do that. For 500,000 years, Mount Etna has been building itself into Europe's mightiest active volcano. Layer upon layer of lava, ash, and volcanic debris has stacked into a mountain that sprawls across 1,190 square kilometers. The sheer mass warps the Earth's crust beneath it. For 27 centuries, humans have chronicled Etna's fiery outbursts. There have been over 60 flank eruptions since 1600 alone. Those spectacular displays light up the Sicilian night and draw millions of tourists who flock to witness the seemingly tame giant. Cities creep up its flanks. Farms flourish on its fertile slopes. The volcano appears conquered, its hazards understood and managed. But we were watching the wrong battlefield. Italian scientists blanketed Etna's surface with the most sophisticated monitoring network on the planet. GPS stations track every millimeter of ground deformation. Seismometers detect the faintest tremors. Thermal cameras map heat signatures. Gas detectors analyze chemical emissions. Satellites orbit overhead, watching the volcano's every twitch from space. The monitoring is so comprehensive that scientists can predict eruptions days in advance. Tour operators schedule trips around the activity forecasts. The mountain seems transparent, its secrets laid bare by technology. Except we could not see where rock met ocean. Until marine geodesy arrived, every sensor fixated on the parts of volcanoes that poke above the waves. Surface instruments gamely tracked Etna's flanks, while beneath the whitecaps, an unseen disaster gathered force. The ocean hides the largest portion of the volcanic structure. The underwater slopes are steeper, less stable, sitting atop a foundation that should terrify anyone who understands geology. Here is Etna's fatal flaw. The African and Eurasian tectonic plates collide directly beneath the mountain, creating a fractured foundation perfect for magma's ascent, but catastrophic for stability. Those same forces cleave fissures through the edifice, leaving it teetering atop weak marine sediments. A titan with feet of clay. The breakthrough came when Dr. Urlaub deployed acoustic monitoring on the seafloor. Sound waves travel through water, measuring distances between transponders anchored to the seafloor. Changes in distance reveal ground deformation invisible to satellites and GPS networks. The technique captures what every surface instrument misses, and what it revealed sent shockwaves through the scientific community. Billions of tons of volcanic material sliding seaward. The underwater flank slipping fastest at its submerged fringes, easing toward motionless near the volcanic center. The exact opposite pattern from magma-driven deformation. This is gravity at work. Relentless, unstoppable. Operating 24 hours a day, 365 days a year, pulling the mountain apart 1 centimeter at a time. Catania, Sicily. Population 300,000. Home to families, businesses, schools, hospitals. All sitting unknowingly in the direct bullseye of Mount Etna's collapsing underwater flank. The city sits mere kilometers from the southeastern slope that is sliding toward the Mediterranean abyss. When that flank finally lets go, Catania measures survival time in minutes, not hours. Taormina and Syracuse stretch along 100 kilometers of vulnerable Sicilian coastline, tourist destinations, historic cities, tens of thousands of residents who have no idea they are living on a tsunami firing range. And here is the problem that keeps emergency planners awake at night. No existing warning system can squawk fast enough to outrun a landslide-generated tsunami. Earthquake tsunamis travel at predictable speeds. Seismometers detect the quake, warnings go out, coastal populations evacuate. The Pacific Tsunami Warning Center has this down to a science. But landslide tsunamis are different, faster, more violent. The initial wave can reach nearby coasts before detection systems even register the collapse. Evacuation infrastructure gets overwhelmed before anyone realizes the danger is real. Zoom out from Sicily, and the dominoes stretch across the entire Mediterranean. Malta sits 45 minutes from impact. The entire island nation has nowhere to retreat inland. Ports, airports, population centers, all vulnerable. Greece and southern Italy face 1 to 2 hours to inundation. Sure, the waves weaken with distance, but weaker is cold comfort when a 10-meter wall of water is redecorating your coastline. The infrastructure choke points tell an even more disturbing story. 1/3 of the world's maritime commerce traverses Mediterranean waters. The Suez Canal's jugular vein pulses perilously close to the threat zone. Underwater internet cables snake across the seabed, carrying the lifeblood of Europe's digital economy. Ports handle billions in trade. Refineries process energy supplies for entire nations. Roads connect coastal communities that have existed for millennia. all woefully unprepared for a volcanic sucker punch from across the sea. Compare this to Hawaii's volcanic collapses. Massive landslides scattered debris fields across uninhabited Pacific waters. Etna's neighborhood is disturbingly different. There is no empty ocean to harmlessly swallow a mountain's collapse. Instead, some of the planet's most densely populated seaboards lie blissfully unaware that a Titan's seaward stumble could drown millions in minutes. Hawaiian volcanoes hold the blueprint for what happens when massive volcanic flanks surrender to gravity. Landslides dislodged 5,000 cubic kilometers of island into the Pacific's depths. Debris fields spread across the ocean floor for hundreds of kilometers. Some deposits rest at depths of 5,000 meters. Evidence of collapses so violent, they reshaped entire ocean basins. The tsunamis generated by these megaslides scoured the entire Pacific Rim. The collapses happened in minutes to hours, not the slow geological timescales scientists once assumed. Ritter Island, 1888. A volcanic island off Papua New Guinea became a preview of catastrophe. 5 cubic kilometers of rock collapsed into the sea in a single event. The resulting tsunamis killed thousands. Waves reached shores from New Guinea to the Solomon Islands, traveling across ocean basins with terrifying speed. The entire island's geography was permanently reshaped. Warning time for the nearest populations was effectively zero. Kilauea demonstrates that this is not ancient history. Hawaii's most active volcano is steadily rearranging the Pacific floor through ongoing gravitational failure. The south flank moves seaward at 10 centimeters per year. Scientists monitor the movement closely, but cannot stop the process. The 2018 eruption triggered accelerated flank movement, proving how volcanic activity can push already unstable slopes past their breaking point. The pattern emerging from these collapses is unmistakable. They are all driven by the same relentless force, gravity itself. They show acceleration away from the magmatic center, just like Etna's seafloor measurements. They occurred faster than prediction models suggested possible. Critically, none were successfully predicted using surface monitoring alone. The collapses announced themselves only after they began. But here is what makes Etna exponentially more dangerous. Hawaiian collapses plunged into deep, uninhabited ocean, thousands of kilometers from major population centers. Etna faces densely populated Mediterranean coastlines. Shorter distances to cities mean less warning time. Complex underwater topography could focus tsunami energy toward specific coasts like a lens concentrating light. Multiple countries would be impacted simultaneously, overwhelming international disaster response capabilities. The lesson from geological history is brutal. Volcanic collapses are inevitable. Every volcano built on weak foundations eventually fails. The question is never if, the question is when. 5 sensors. That is all that caught Etna's 2017 underwater movement. 5 seafloor transponders were positioned across one of the most dangerous volcanic slopes on the planet. A geological peephole into a massive underwater structure that could generate a Mediterranean-wide catastrophe. The revolutionary discovery that rewrote volcanic physics happened with scandalously scarce tools. It was pure luck that the sensors were positioned to detect the movement at all. Now zoom out to the global picture, and the monitoring crisis becomes terrifying. No systematic underwater surveillance of volcanic flanks exists anywhere on Earth. Satellites cannot penetrate the ocean to measure submarine slopes. Surface GPS networks miss entirely underwater deformation. Seismometers detect earthquakes, but not slow gravitational creep. The technology that caught Etna's collapse in action remains deployed at exactly 1 volcano worldwide. Meanwhile, the roll call of unmonitored coastal volcanoes reads like a travel brochure. The Canary Islands include La Palma, where Cumbre Vieja is considered a major Atlantic tsunami threat. The Azores host multiple active volcanoes sitting in busy shipping lanes. In the Caribbean, Montserrat, St. Vincent, and Martinique all have substantial submarine flanks. Dozens of Pacific Island volcanoes are built on weak sediment foundations. Even Etna's Mediterranean neighbors, Stromboli and Vesuvius, have underwater portions that remain completely unmonitored. If other coastal volcanoes are skidding seaward unseen, we simply would not know until mega tsunamis scour coastlines clean. The candidates list includes some of the world's most popular tourist destinations. These are volcanic mountains that millions of people assume are stable, simply because they look peaceful from above the waterline. Climate change accelerates the crisis in ways most people never consider. Rising seas increase hydrostatic pressure on volcanic rubble piles. The additional water weight compresses already unstable slopes. Intensifying storms jackhammer shaky flanks with wave action. Pounding rains pump pore pressure into every crack and fissure. Warming oceans expand seawater volume, squeezing submarine slopes from all directions. Bit by bit, climate change tweaks the odds in gravity's favor. The resource allocation failure is staggering. Millions flow to monitoring surface eruptions that rarely kill anyone. Minimal investment goes to underwater surveillance that could save thousands. Political will evaporates when disasters exist only as future possibilities. Funding materializes after catastrophes occur, never before. Scientific proposals for expanded monitoring networks are repeatedly rejected as too expensive. And here is the most maddening reality. No one knows how fast Etna is moving right now. Another 4 centimeters this decade, this year, this afternoon? Without continuous monitoring, we are flying completely blind. When Etna's southeastern flank finally collapses, and it is a matter of when, not if, the death toll projections are catastrophic. Eastern Sicily faces tens of thousands of casualties in the initial wave. Malta's entire coastal population sits in the impact zone. Greece and southern Italy count thousands more in subsequent hours. No evacuation plan exists for landslide-generated tsunamis. Emergency responders would be overwhelmed before the first sirens finish wailing. The infrastructure destruction follows a brutal timeline. Hour 1, eastern Sicilian ports are obliterated. Shipping operations cease instantly. Hour 2, Malta's economy stops functioning. Airports are flooded, power grids are destroyed, and communication systems are severed. Hours 3 and 4, Greek islands and southern Italy are pummeled by waves that weaken with distance but remain catastrophic. Mediterranean shipping lanes are blocked by debris for months. Underwater internet cables are severed, disconnecting digital infrastructure across 3 continents. Refineries are damaged or destroyed, triggering an energy crisis that ripples through European markets. The economic cascade effects dwarf the immediate destruction. Mediterranean shipping handles critical global commerce. Disruption lasts for years, not months. Insurance industry losses are estimated between $50 and $100 billion. Many insurance policies exclude tsunamis generated by landslides, leaving homeowners financially devastated. The tourism industry collapses across multiple countries. Sicily's $1 billion volcanic tourism economy vanishes overnight. Agricultural losses hit coastal regions. Real estate values plummet throughout the entire tsunami zone. GDP impacts for Italy, Greece, and Malta reach catastrophic levels. A political crisis erupts before the water even recedes. International disaster response coordination fails under the scale of a simultaneous multi-country catastrophe. Blame allocation begins immediately. Why was no warning system deployed when scientists identified the threat in 2017? Mass migration from destroyed coastal regions overwhelms refugee systems already strained by climate displacement. EU emergency funding debates paralyze governments as nations argue over cost distribution. NATO disaster response activates for the first time for a natural disaster. Here is the brutal calculus that politicians refuse to face. A comprehensive underwater monitoring network costs $500 million. Early warning system deployment runs $2 billion. Disaster response and recovery exceeds $200 billion. The choice is invest now in prevention, or pay catastrophically for repeated disaster response. When the collapse occurs, and scientists have been warning since 2017, who bears responsibility for the thousands of preventable deaths? The solutions exist. The technology is proven. Only political will and funding stand between Mediterranean populations and catastrophe prevention. Deploy a comprehensive underwater monitoring network around Etna's entire submerged flank. Dense arrays of seafloor transponders would measure continuous acoustic ranging. Real-time data transmission through fiber optic cables would deliver information to warning centers. Redundant systems prevent single-point failures. The network provides constant surveillance of flank movement, detecting acceleration before collapse occurs. Cost: $500 million over 5 years. That is the price of 2 fighter jets to potentially save hundreds of thousands of lives. Tsunami early warning systems must be tailored specifically to landslide events. The physics are different from earthquake-generated tsunamis. Faster wave propagation demands faster warning dissemination. Automated trigger systems activate based on seafloor movement thresholds. Direct communication pipelines must connect to emergency services and civilian populations. Smartphone alert integration is essential. Coastal siren networks must have backup power supplies. Deployment across the Mediterranean costs $2 billion. That is less than the economic damage from a single moderate collapse. Supercomputer modeling war games every possible collapse scenario. Simulations calculate tsunami propagation for different failure volumes. Models identify the most vulnerable coastal segments. Evacuation routes are designed based on actual wave physics, not guesswork. The modeling updates continuously as new movement data flows in. Investment: $100 million for comprehensive programs that provide the playbook for survival. International coordination frameworks must be established before crisis strikes. Mediterranean nations must share data protocols and alert systems. Cross-border evacuation agreements and coordinated disaster response planning are essential. Regular tsunami evacuation drills turn theoretical plans into practiced reality. Political mechanisms for rapid decision-making are needed when seconds determine survival. Monitoring must extend globally. The Canary Islands, the Azores, the Caribbean, and Pacific Islands are all at risk. Every high-risk coastal volcano needs underwater surveillance. International scientific collaboration must share data and expertise. A global database tracks volcanic flank stability worldwide, identifying threats before they become catastrophes. This is the urgency argument politicians cannot ignore. Etna's movement is documented and ongoing. Every day without monitoring is gambling with thousands of lives. The cost of prevention is microscopic compared to disaster response. Technology exists and works. The only missing ingredient is the decision to act. Face the threat now with preparedness, or face catastrophe later with regret and body counts. The choice should be obvious. A pall of dread hangs over Mount Etna's every shutter since May 2017. 4 centimeters in 8 days. Mountains are not supposed to move at that clip, but the data does not lie. Etna is flirting with a deadly cliff of no return, and the problem is brutal. No one knows how close the volcano sits to catastrophic failure. The transition from slow creep to sudden collapse could span centuries or seconds. Current underwater monitoring remains woefully sparse, a geological peephole when comprehensive surveillance is required. Meanwhile, the creeping culprit keeps scientists guessing. Another 4 centimeters this decade? This year? This afternoon? The answer hides beneath Mediterranean waves. Next time Etna makes headlines, it may not be lava, but a hydrogeological hammer blow. We are not powerless. Solutions exist, technology is proven, but we must pry our gaze from the spectacular fireworks to face the real threat. A mountain with a mind to meet its maker, one sinking centimeter at a time. How many other volcanic time bombs are ticking invisibly beneath the waves? When Mediterranean titans fall, will we have acted in time?